do the Monte Carlo approach for the wild mana collection. And yeah, I'll have about half an hour to 40 minutes of streaming time, and I hope we can get something out. If not, then the next stream. All right, let's go. So early on, when I ran my code, the only thing that I did was to do a few more helper functions. The first function is called move towards, which basically uses vector magnitude in order to calculate the next velocity x and velocity y to go to. Okay, after that, I also do predict next position velocity, where I predict the next monster's position and velocity. Okay, so this is something that needs to be improved on. Okay, because what we want to do is we want to not only output the next position and the next vector, we want to output like the list of all future positions of this monster so that we can plan our heroes to do some Monte Carlo and optimize the amount of mana we collect. Okay, because I really feel like if you optimize the mana, you will have an advantage in the spells later on, and that will be another stream I believe to optimize the spells. Maybe you can even do it using a Monte Carlo method. I have no idea. Yeah, so let's see whether it works first. So this was what was done just now using the updating the position of the monster based on the velocity vector, then calculating the whether or not it goes to the base, and then after that do some form of like adding the position and so on. Okay, so actually what we need to do here is very simple. I realized something. Okay, we don't really need to do all these steps. Okay, if the monster did not like transit like within this base here. So if the monster is already within this base itself, okay, the monster's velocity will automatically be the same velocity as what it had before. Okay, but it doesn't matter. We can just run this loop a few times in order to get it. Okay, so what I want to do now is I want to just okay. So this is my predict next position code. Okay, let me just expand this a bit. Okay, yeah. I hope y'all can see this. Yeah. Okay, I think y'all can see it. Okay, so I have my next position prediction code already out. Okay, and what I want to do is I want to update it not just for the next future position. I want to update it for like X number of positions for all these monsters, and maybe not just for important monsters because that's kind of restrictive. Important monsters is like when there's a threat to your base. Okay, so I think we also should consider monsters that are roaming around. Okay, because our aim is to maximize wild mana. We don't want to just limit it to important monsters. So what we can do is we can do like this: important monsters plus monsters. Yeah, that's cool. I mean, yeah, that's actually what we need. That's all we need to do because these two are lists. So if you add two lists in Python, you will get a new list. Okay, something like that. Okay, and then we have future X is this future. Okay, this actually we don't need this anymore. Okay, but I just keep it there in case. So what I want to do is I want to append a list of future positions for the monster, maybe like the next 5 positions. Okay, I mean depending on how many Monte Carlo. So I don't need the next velocity actually because that's not important for the calculation. What's important is the position of the monsters. So monster future pause, we have this. So we append like the distance of the future position plus like maybe future pause, which is basically the this one. This was our old function. Okay, now maybe I mean this okay, I'll have to change this somehow. Okay, let me think of how to change it. So this one was working, so I can just hide this. Okay, so over here, this was to sort to find like the nearest monster. This one need to change. Okay, let me just put a to do here. To do, change this to support Monte Carlo. Okay, so instead of having the monster's future pause like that, okay, we actually want to do something. We want to find out all the future positions of your monsters. So okay, how do we do that? Okay, maybe I have a variable here. I have a variable called look ahead steps. Maybe I put it as 5. Okay, so I look 5 steps ahead. So what we do is like this. We have this thing here. Okay, so I will not do this win thing right now. Okay, this one is it will make the bot weaker, but I believe this win thing should be uh, it can be done within the Monte Carlo itself. Okay, so I'll just take it out. So what we need to do is, well, this is a double for loop, so it will be like maybe if there's 20 monsters here and then there's like I don't know five times there's 100 iterations of this. I hope Python is fast enough. Okay, not we have to use this like we have to code this in C++ instead. So what we do now is we do the for I in range look ahead steps. Okay, then we can do this. Okay, so we do have this each position, each trajectory. Okay, that is basically we can just put like next pos equals to each. Okay, so we have this. Okay, very simple look ahead. Okay, and then basically this thing here inside here, it should be next pos, next velocity because we are updating it. Okay, so in the monster future pos, okay, what we should do is we should update all these ranges here. So let's just do this. Okay, let's just put the monster pos. Yeah, let's have a monster pos variable, and then what we do is monster pos. Okay, so here this one, if I is 0, then this. Okay, in order to give us our first time step. Okay, then we want to do this and then update the position of. Okay, actually I don't need to put this inside the loop. Let's undo that. Yeah, we could just jolly well start with the monster position as our next position, like that. Yeah. Then for every loop we do here, we do a monster pos. Okay, so this next position actually, oh, actually we don't need to do this because we are only interested in the monster's next position. So we can just do like that. Monster pos dot append equals to a empty loop monster pos append next position, and that's it. So we can actually print out the monster pos here in order to find out like what to do for that monster, like what are the future positions for this monster. So monster pos append distance future pos base pos future pos. Okay, this one okay needs to be deleted. Okay, because we don't have this anymore. Okay, so we need to change this now to support Monte Carlo. So this gives us a list of the monster positions so far. Okay, it doesn't tell us anything else. It just tells us the list of positions. Okay, at this point of time, I think I would like to just check whether this works. Okay, we just check by just printing out this. So there's no monster future pos. Take it out. Okay, let's just delete this whole thing. I mean, if I need to, I can just refer again in the previous code. Okay, so let's just print the monster position for each monster. And then over here, monster future pos, append monster pos. Okay, so let's just print here. So over here to attack, let's just put the attack option as force all the time, okay, so that we don't attack. Or out attack, this one, yeah, we don't do anymore because this it's kind of horrible. Yeah. Yeah, let's just do the if to win equals to this. Okay. Okay. Okay, but we can keep the all attack thing, I guess. Yeah, because later on we might want to do a case whereby one of the heroes go to the opponent's base and does wax him. So we keep all attack for a while. Okay. Um, this is the whether or not to win. Okay, and the win will always be force because I deleted away that line here already. That says to be true. So this won't happen. Then we just need to do this attack. So I just want to maximize my WoW mana again. Okay, I will lose a bit of competitiveness in the board because I don't have this defensive mechanism anymore of this. Okay, but I want to see whether I can imbue it later using heuristics. So what we want to change is we want to change this one here. So the all-out attack here. Okay, the heroes, we have three heroes. Okay, let us just do it such that all three heroes move at the same time, like what we did before. Okay, but we move towards a Monte Carlo position. Yeah, so not a fixed heuristic position like that, but we use a position that has been determined by the algorithm. So I'm not too sure whether this will work better than this original one. Okay, but let's see. So to attack equals to force. Okay, this will always be true actually because okay, we will always have a monster to attack. So let us change this function. Check where to move heroes to in order to maximize wild mana. Okay, so let us see first. How far can the hero move? The hero can move a total of oh, monsters is 400 units. Okay, we already have 400. Okay, the hero will move. Where's the hero movement? Hero will move. I think 800, right? Hero move 800. No, 800 is the 800 units of damage where the monsters will sustain. Hero will move 800. Okay, so we want to do the Monte Carlo approach here in order to do the attack. Just delete this thing here. I'm actually deleting a lot of my code here because I'm trying to do a new something new. So we want to now change this, okay, to move the heroes to maximize the wild mana. So I have a list of monster future positions here. Okay, maybe what I'll do first, okay, is I just want to print the monster position, okay, with a range of 5, okay, and then like let's just see whether or not it has predicted the next 5 positions of all the monsters correctly. Okay, let's see what happened here. Division by 0 in line 32. Oh, okay, it means the monster has reached the end goal here. So okay, no biggie. We can just like make sure that we just make it 0. Else next angle equals to this. Okay, sure. I mean, I didn't expect a 0 position, but it appears that you can have a 0 position if you look forward enough. Okay, so you see, I died pretty fast because my hero is actually doing nothing right now. It's just letting the monsters go in. I just want to see whether I predict the monsters correctly. Okay, so we do have a monster here. One, two. Okay, looks like I'm printing it many times. Okay, so maybe I put the printing code too far out. Okay, let's see. Yeah, I put it here in the for loop. I should be putting it outside of the for loop to just take a look at whether the monster's position is predicted correctly. So let's see. Okay, so right now it's predicting some monsters. Okay, I don't see anything. Ah, yes, here. 5487 4343 5279 5071 4863 4655. Okay, let's look at the other one because this is going near the base. 367 894920 824521. Okay, let's try that. Okay, later it becomes 683726. So maybe let's just search 1, 2, 3, 4. Okay, was that correct? Okay, so it should be 683726. Kind of didn't reach that. Okay, 894920 824521. Okay, 894920 824521 754123 824521 754123. Okay, so over here there's a rounding error already. Here it's up to 22. Okay, so we need to fix this. Okay, there's 1 pixel difference. Okay, and that's probably because of, I don't know, I don't think it's because of this, but I realized something. We don't need to calculate magnitude at all. Okay, because it turns out the monster only moves 400 distance. So let's see. Where's my magnitude calculation? Here. Yeah, we can just make this to be 400. I wonder if this would actually solve that problem already. Let's try. Okay, I need my prediction of the next 5 positions to be quite accurate so that the Monte Carlo approach can work. Okay, so let's see. Okay, so let's look at this monster. 2865 4129. Okay, eventually it will reach to 2030 2782. 1, 2, 3, 4. 20230 2782. Very good. Okay, so actually all this looks accurate. So if I do another 4 steps, it should be 1089 1491. Oh, very nice. So eventually it will reach like 147202, which means that it will be destroyed. So once it reach here, okay, the next few positions it will be destroyed. This at the next this move it will be destroyed already. Okay, so as you can see, it becomes 0000. Okay, because what will happen is that it will just be updated such that it becomes minimum 0. Okay, that's great. Let's move to the next monster. The next monster is here. The next monster is here. 1294450. Okay, so this is correct. Is this correct? 1184051. Okay, looks like after I change the code, it's kind of working. Okay, let's look at this bug here. 454759 1757. Okay, after 4 turns, it should be 3326 1484. 2, 3, 4. 3326 1484. So it is working. It is working. So we try one more. We try one more. We try this one. 48441093. And this becomes 3284 741 after 4 turns. Okay, looks like all the monsters positions are working. Okay, very nice. Okay, now let us start coding the Monte Carlo proper. Okay, where was I? Let's see. So this monster future pause will contain all the future positions for each monster. Okay, and that will be basically what we will look into. So what we can do here is like that. If length, yeah, this one, then to attack will be true. Okay, and not just that, we need to specify where to attack. So over here, move this one, we cannot use this anymore. So we just change this to Monte Carlo X, Monte Carlo Y. So over here, we do a function, and then what we do, we append the monster future pause here. And then we also need to append our heroes. So our heroes is under my heroes. So what we need to do for my heroes is just basically put in the position. Over here, we will just treat all three heroes to be the same position. Okay, we just want to. Why is there an error for this? My heroes dot append my deck. Oh, because of all the different positions here. Yeah. So maybe what we should do is we should append the position for all three heroes separately. Okay, so we define a function like that, which returns Monte Carlo. Okay, just to make sure that it kind of works right now, let me just define the Monte Carlo here. Maybe we quite define Monte Carlo while mana. Okay, because maybe we want to do Monte Carlo for like uh maybe we want to do Monte Carlo for other stuff next time. Yeah, like spells. So this is for wild mana. So we define the Monte Carlo wild mana to take in what do we have here? To take in the future position and also the hero's position. My hero, maybe we should just put this in a tuple so that we can easily take my hero cost. Okay, takes in the monster future positions and my hero's position and returns it the best position for each hero to go to next time step. Okay, so maybe over here is Monte Carlo Sims. Number of Sims. Okay, so Monte Carlo Sims over here for. Okay, so we have a future position vector which we actually won't change. Okay, we only have this hero position vector which also we won't change. Okay, these are all the starting positions. Okay, what we will change is we'll change the heroes. Okay, so like what we will do is like my hero. Okay, let's just put my hero equals to. Okay, let's do a very rudimentary one where we just go towards the nearest monster, I guess. Yeah, so maybe what we do is my hero equals to my hero cost. Okay, my hero one equals to my hero. Okay, relations for the top few positions for mana. Okay, so how do we do this? Okay, so we have to rest random. Okay, let's not do the nearest. Let's just do Monte Carlo already. So we have three heroes. The positions are here. Okay, what we want to do is reset the initial positions. Okay, then over here we have a look ahead steps also. So look ahead steps equals to 5. Let's just put this here. Maybe the Monte Carlo streams can be 10,000 look ahead steps equals to 5. I wonder if this will run in time though. Yeah, maybe 100. I don't know. Let's look at 100 first. So and range this, and then initial position will be my hero 1, my hero 2, my hero 3 equals to my hero pause. Okay, and then total wild mana equals to 0. Okay, so we do have like best hero pause equals to, maybe we just set it to be my hero pause first. Okay. So at the end of the day we just return my best hero pause. Okay. And then we have like best wild mana equals to 0. Okay, then do the simulation, check if it is better than best. Okay, so we have this my hero 1, my hero 2, my hero 3 equals to, okay, maybe what we do is like this. Yeah, we set an initial position for each of the heroes like that. Okay. 1, 2, 3. So if, okay, total wild mana greater than best wild mana, okay, then what we'll do is we will just append, we'll just put the best hero cost equals to my hero 1. Okay, this one I think we can just put it as a tuple, my hero 1 0, my hero 2 0, my hero 3 0, which is the first position that they have here. Okay, so this is the first position that we have. Okay, and the first position actually, oh, actually the first position need not be this one. Okay, I'm just thinking, how do I do this? Maybe just one. Yeah. For I in range, look ahead steps. Okay, we will do the simulation where we will just move the hero randomly. Okay, so in the future pause here, we do want to have a future pause that is segregated by time step actually. So maybe in the way we do our future pause over here, we need to change it a little bit. So is a monster pause dot append what, right? Maybe what we want to do, okay, instead of having this, we have a monster future pause as maybe a dictionary. So we just have a dictionary whereby it's like I is to nothing, for I in range, look ahead steps. Yeah, so that we can reference our monster dictionary by time steps. Okay, that will make things easier. Okay, and then over here in my monster position, what I'll do is I'll append this uh this monster pause here in the look ahead step. What I'll do is we have no need for this anymore. We can just do monster future pause I, because I is already here. Okay, dot append next pause. We don't need this. We don't need this. So in the end, I will have a dictionary of the future positions of the monsters at every time step. Yeah, let's just do this. Okay, so now what I want to do is I want to go back to my code here to do the wild mana positions. So towards one of the So you can see that this future pos has a vector now, has this. So let's see whether we can do like random dot choice for array. Okay, random dot sample, I think. Random dot sample to choose without repeating elements. So we can just do like random dot sample sequence comma n from a sequence without repetition. So random dot choice, random dot sample sequence comma n. Yeah, we can do this. Okay, so we just sample one. Yes, generate n samples from a sequence. No, we don't need this. We do a random dot sample. Okay, so what we'll do here, okay, we'll just do this. Okay, so okay, so we do have my heroes being like that. So it's kind of irritating because we have to loop this many times. But I think there's only three heroes. I think it's fine to do this loop. So what we can do is we can do this. Okay, so okay, let's see how do I do this. Okay, so we do randomly sample a future position. We move the hero towards that position. So where's my move towards function? Here, move towards next position. Okay, here's sample one. Next position, hero position, which is like that, and then with a distance of 800. Okay, so that should do it. So this is for one hero. Okay, so this is for my hero one. Okay, I'm just thinking whether or not I will want to do like my hero I. Okay, where basically we can just have my hero as a dictionary like that, and then we could do like my hero I equals to my hero pos I like that. Maybe this will be better for I. Okay, then this one you need to do like for j in range 3, my hero j equals to this. So we initialize our heroes like that. Yeah. Then we can simply do like my hero j. Okay, so for j in range 3 is the number of heroes. Okay, move the hero randomly towards one of the monster positions. Okay, and then we move the hero towards that. Okay, then after we move towards this, move towards returns things. Okay, it returns the position. Okay, it returns the velocity vector heading from, yeah. So it returns this is the velocity vector, which we then can use to basically add up. Okay, we can add up the velocity vector here. So what we do is we have this move towards. Okay, so the next position over here, we can just put like my hero next pos equals to like this, next pos 0 plus next val 0. Okay, next pos 1 plus next val 1. Okay, I guess this is basically just the next position for the hero. And then after that, we can then just check if the hero can attack the monster. Okay, so this is very rudimentary. So in order to check whether the hero can attack the monster, we can just simply use the distance function that we did earlier over here. Distance. If this, okay, my hero next position and the monster position. So we actually do need to have the next position. We do need to have this list of monsters that can be attacked actually. So okay, so it's like this. For so actually it might be more complicated than I thought it would be, because you will need to have the health of your monsters so that you can see if the monster has been destroyed by a hero or not. Okay, but for now I think I won't add it. I will just do without it. I'm just very a bit concerned because like in order to do the Monte Carlo sims, I need to do locate steps. I need to do for each hero. That's like this alone. Like let's say this is five times three. This 15 simulations, and this 1,500, and we only have 15 milliseconds. I'm not too sure how many sims we can do, so we got to be smart about it. Okay. So maybe that optimization can come later. But right now, let's see whether this works first. We check whether the hero can attack the monster in the future pause. So you see your total wild mana is here for each in future pause I. Okay, so we can do this actually. Yes, we already have my hero next pause here, right? So we can do this independently of each hero. So for each in future pause I, okay, what we will need to do is we will need to okay each in future pause I, we will just check okay whether or not the hero can attack the monster, and then we add the total wild mana if it can. So if distance, okay, then over here for J in range 3 again, okay, if distance, my hero, if distance each, and then my hero next pause. Okay, we actually didn't add this into like, we didn't append this into my hero, right? So what we can do is we can just append this my hero J dot append the next position. So maybe over here this can be my hero J -1, which means the last position. Okay, if this distance is smaller than or equals to 800, okay, we need to do a times because I didn't do a square root for my distance. If the distance can be, if it's within the range of, okay, so over here we need to like maybe to do add in the deduction of health for the monster. Okay, and then what we want to do next is we want to also, okay, so this is a to do. What we want to do is if this distance is true, okay, we want to basically add in a total wild mana as 1, okay, because that means the hero will have gained, okay, maybe 2 because we gain 2 wild mana for each attack, right? But it doesn't matter in this optimization because we will basically be the same. You add 1 or add 2 is relatively going to be the same when we do the simulation. Oh, it's only 1 point. I thought it was 2 points actually. Yeah. Or per damage dealt. Okay. I think the hero will do 2 points. Yep. So it's +2. Okay. Then we will just basically check whether this wild mana is better than the best one. Okay. Hold on. Okay. Let's see if this distance smaller equals to 800. Yep. Okay. All right. I think this code should be fine. It's better. Then we just add in the next position of my hero's position. So my hero initially started off with their base positions, and then I just add in his positions here, and then we return best hero pause. Okay, so in the best hero pause, what we get, yeah, so we do have like the hero position here. uh Maybe we can just like put like h1 h2 h3. And what's this? It's not defined. Monte Carlo wild mana is not defined. Did I define it here? Okay, apparently this is indented wrongly. Let's move this back. Let's move this back. Where is it? Let's move this back. Okay, we move it back here. We have Monte Carlo wild mana now. Okay, and we have H1, H2, H3. Okay, what we can do is basically like that. Now we can just do in a dictionary like that so that we can HI0, HI1. Okay, let's see. I'm pretty sure I have an error. Quite sure about it. See whether okay, random is not defined. Okay, sample larger than population or is negative. Okay, so there will be a case whereby this future pause will be having no monsters. So if it has no monsters, then if there's a monster, then do this. Else, okay, next position will just simply be the my hero position J -1. It will just be the previous position. Let's play this code again. Okay, greater not supported between instances. Oh, silly me. This bracket should be like that. I wonder how long is my code already. Okay, integer object is not subscriptable at line 33. Okay, 106. Next pause, my hero J. Okay, I think might have put it. This one should be my hero J instead of my hero pause J. Okay, so here would be my hero 0, my hero 1, which I forgot to change just now. Hero 2, like that. This index out of range on line 35. Okay, there's a lot of problems with this function here. So let us just see what is being printed here. So print next pause, my hero J -1. File equals sys.standard error. Let's just see what's the issue with this statement here. Okay, as you say, index out of range. So let's see what's wrong with this. Okay, so I think I see the problem. Next position here, okay, is a random sample like that. The random sample is in a bracket, so maybe that's why it did not. I want just the tuple without the square brackets outside. So let's try again. Okay, this time it reached 110, which is a great sign. It means that the code is sort of working. So yeah, let us enjoy and see like the performance of this agent. I don't suspect to be too good because I didn't prioritize like defending the base at all. Okay, just play this. It's very funny how he just like helped me defend my base. As he didn't bother defending. So that's something that needs to be added in. But right now, the Monte Carlo simulation seems to be trying to maximize the WoW mana a bit. Yeah, I mean, it looks like it's kind of working, isn't it? Like, it looks like the heroes are kind of attacking. It's just that it's kind of not prioritizing the monsters that are attacking the base. Okay, so perhaps what we should do is we should give like more weights to the actions that actually lead to. We could do a weighted sample where we sample based on the monsters that are near the base, I guess. Yeah. Yeah, so I do have three randomly wandering heroes right now. Okay, they don't really prioritize defending the base at all. They just like, okay, see, like this kind of movement up down up down up down is kind of like not very consistent. You see, I mean, you can move there, yes, no problem. And then at the end of the day, after I do the Monte Carlo, it's supposed to return back to like a certain base area, which it doesn't. Okay, so maybe this is not like optimal yet. Let's see how much we can up it by. So this was for 100 Monte Carlo positions. Let's try it up 10,000 and see whether it can still run or not. I have no idea whether this can work, but yeah. Okay, so there's a few things that need to be implemented. One is, oh no, I think timeout. Yeah, so it looks like Python kind of cannot simulate a lot. Okay, so maybe we simulate up to 1,000 and see how it goes. Or even 1,000 is not possible. All right, maybe I'm printing too much. Let me just remove my prints. So like this was to just check whether I can go to the next position. I can remove this. I mean, there's no need to print out all this. Let's see whether I can do 1,000 simulations. Okay, so you see, I did not go to like a rest position or something, which I should actually. Not provided 3 lines in time. Yeah, as I feared, the timeout is quite severe for this using Python. So you see, when I only have one enemy here and it cannot even do 1,000. Okay, let's try maybe 500. Okay, I don't know how much, but it could be. I could use the time function also to just before it times out. Okay, let's see whether it time out here. Ta-da. It's kind of like wandering around the place actually. Not sure whether just a simple rule base would be sufficient because like you see if I will only have 500 Monte Carlo sims. Okay, let's just go down to maybe 200. Maybe I don't have to look ahead so much. I can look ahead like maybe 3 steps. Because it's kind of doing some myopic short-sighted. I see now it looks like it's performing pretty alright. Uh, Maybe the look ahead steps I just need to reduce it because like a lot of times it's like wandering around doing nothing while I want it to like be attacking actually. Yeah, kind of want it to maximize this wall mana thing. Yeah, I have a feeling that the reason why the sims are taking so long is because of this distance check here because we need to check all the future positions of the monster, which can be a pain because if we were to do this, assuming like there's 20 monsters, this is like 20 times 3 already. Yeah, I could use a limit by time here. Yeah, and I'm just checking whether this works because actually it looks like the performance isn't like super good. I think the original rule base might be better. Just having three at the same time. Yeah, I'm just experimenting with this. So I think this check because every time when we do a new position for the hero needs to check the distance for all the monsters in that list, which can be very time consuming because imagine if your monsters there's a lot of monsters you have to run this distance check all the time. Okay, which can be rather annoying actually. Yeah, in terms of the runtime. Yeah, but I think I have no choice. One thing I can do is I can limit the monsters that are present in this um in this here. Let's see. We can set a threshold for the monsters to be considered. Okay, for the defense because I don't think we need all the monsters. So like maybe what we do is we just do important monsters first. We don't do all the monsters. We just do important monsters. See, I'm also thinking of reducing the look ahead steps. Okay, maybe to 3. So over here we have Monte Carlo Sims. Maybe the look ahead. Yeah, this is the problem with no neural networks. You see, like if you were to use like stuff like Alpha Zero or stuff like that, you can do as many iterations as you want. Okay, but the problem is you don't have the flexibility to do the Monte Carlo look ahead if you were to do it just in runtime like this, especially with Python. Python is quite slow a language. Okay, so it does seem that it's doing okay. All right, I just care about the important monsters only, and then it focuses quite well on it. Okay, not exactly. See, it's not defending all this. This is a folly that could be avoided. Okay, so I need to prioritize the monsters that are near the base. So maybe if a monster is uh already known to be attacking the base, we put more heroes there. So right now I'm only targeting monsters that are like important to me. Okay, it's not exactly very optimized. Okay, so there's another thing that could be done is that instead of heading straight to the monster, we could head to like some sideways position, or we can cast a spell. So all these are potential considerations. So I'm thinking actually the look ahead steps don't need to be so much. So we can do a look ahead step as 3. Okay, and then like over here we can reduce the runtime by. I don't think it's needed to look ahead too much. The only look ahead you need to do a lot is look ahead whether the monster is going to hit your base. Yeah, so let's just make the look ahead steps 3 and then run this and see whether it works better. Okay, so here I think 3 time steps should be sufficient to actually look quite sufficiently deep already to collect wild mana. I mean, this is just for the code of collecting wild mana. So at least it didn't time out. Okay, that's a good sign. I mean, I also reduced the number of creatures that is considering. Okay, so you can see the monster is like they are very short term in terms of their decision making. Like they only go for the near ones, but they never defend the base. So that's something to work on for the next stream. Okay, so also another thing is if there's no monsters, it didn't go to the rest position. So we need to make it such that if there's no monsters, okay, if there's no monsters, this one, if there's no monsters, we just basically go to a rest position. So okay, very simple. If length future pause I is 0, or future pause 0 is 0, then return like maybe a rest position. So it's like yeah, you could do this. Yeah. So this would help to Okay, so I definitely need to program something to help to defend the base. Yeah, definitely need to do that. Okay, so you can see that okay, at least now it's I think it looks like it's defending better. Oh, is this the 6,000 position? Yeah, it is. The base radius is how much? 5,000. Yeah, see, it's not attacking these monsters when it should. It is something that okay, so it looks to me like using the Monte Carlo approach might be a little myopic in nature because each of these three of them, okay, they actually just move towards the. I could just do one of them move to the same target. It might work better rather than all three. See, all these things actually could target. Okay, maybe I should expand because now I only consider three time steps. I can expand this thing to just look at more monsters. Okay, but at least one thing for sure is that it looks like it's attacking something, just just not very accurate. Yeah, I guess there's too many possibilities for three people. Yeah, if we were to do all three in the same position, okay, maybe it might be better. So yeah, maybe all three being to the same position will help to increase the efficiency of Monte Carlo. That's one thing that could be done. So maybe what I can do is I can just do for range one, okay, and then we just repeat this three times. Yeah, so I kind of just do a bit of a tweak in my Monte Carlo. I do all three in the same position. So I think that might be actually better. Yeah, because at least it's like more efficient in terms of killing the monster than all scattered out. Then like that, I also can check less. Okay, so I think there's no need to spread heroes anymore. I just put all in the same like before. Okay, but now what I do is I actually check more. Okay, just check this. Okay, I'm not too sure whether this actually is better than my naive code of just going to the nearest monster. Okay, I definitely need to implement a monster defense check to make sure that it can work. Okay, but now at least it's surviving for like 100 time steps. Not too bad. Okay, so the worry about this particular code is that it can actually lead you to forgo. Is there a fog of war here? It could lead you to forgo like the monsters in your base if you venture out too far by searching for all the monsters. So maybe instead of just searching for all monsters like that, all monsters with a threshold of certain range before the base. You can see that he's also like just searching for the nearest monster here. I'm pretty sure this algorithm is nothing to do with Monte Carlo. It's just finding the nearest ones. So is it we go too far here? We forsake all these monsters here. Okay, so that's the only concern if we were to do stuff like this. But of course, if we just do this by important monsters alone, okay, we survive longer, but we miss out a lot of valuable mana that we could be collecting. Yeah, so I guess I will want to code in like a priority for certain monsters going to the base. I quite like Monte Carlo with just one agent going around. I think it's quite useful. Yeah, maybe not just one agent going around like that. Maybe what we can do is I don't know. Maybe it would be more efficient to do two like that, and then one at the opponent base. I'm not sure about that because we actually need to spread our field of horizon more in order to see over here. Okay, at least this is the only important one. It defended well. Yeah, see now it's going in between two, but it's not decided. See, it's going left, right, left, right, left, right with no priority. So that's something that we don't want to do. Okay, the problem in Monte Carlo is you have not much control of it. I think if it's just one, maybe we could do more simulations. We could do maybe 1,000 simulations. Let's try to do 1,000 simulations because I kind of think that 100 simulations alone for this is kind of underwhelming. Yeah, but if we do the different Monte Carlo sims for all three agents, it's taking too long. That's what we see here. So there needs to be a compromise somewhat. Yeah. So one thing to add is the defense to the base that needs to be added in. Okay. So you see, we don't prioritize this, so it's going in limbo. Like, so it only considers the next three time steps. Okay. Which I think is good enough. It probably will just go to the nearest creature. Okay. So one thing that can be done also is we don't need to just look at the nearest trajectory. Okay, we don't need to just look at the nearest creature. Okay, we can also do like based on a random angle and then do this. So over here, I add a to do here, move towards a random angle instead of the future monster position. So this is actually quite risky because we may move wrongly. We may not move towards a monster. Yeah, so this is something that can be done next time. Okay, actually I've got to go. I'll work on this Monte Carlo sim. I think it can be useful if implemented correctly, with some safeguards to prevent your creatures from coming to your base. Yeah, but overall, I think in this, especially for this game, just going to the nearest monster may already be sufficient to get a strong AI, because there's not much you can do for this. Maybe what you can do even more is to use a form of like, maybe you can use Monte Carlo to decide which monster to attack in terms of like to attack your opponents. Maybe it's better suited to attack your opponents. But to collect mana, I think just my previous code of just going to the nearest monster, nearest to the base, kind of works pretty well. Yeah, so we'll see how it goes. And yeah, thanks for watching. I got to go and see ya.